of
okay,
ice
yeah,
within, you know, and that there are, when you have different etheric effects, let's say, you know, the honeycomb, you know, let's say you put a honeycomb next to it, put a pyramid next to that, the ice forming in the freezer. So they were just putting a pyramid, okay? It had granite, which has got crystalline formations. If you look at crystals and how they form, they literally form in a spiral pattern, okay? The crystal formation is actually in a spiral. So you're actually working on the spin of the particles when you've got a crystal. And crystals can have this type of effect. People put dielectrics and conductors together, they have the same type of effect. So when you have a geometry of a spin, but you also have materials geometry with a spin, or, you know, so the guy who was working with water, energizing water, he was getting the water to spin, and he was getting that energized effect, that energized water effect, you know, that type of ether effect, the type of chi effect. All these effects that people are seeing anomalous behaviors with, a lot of them are associated with spin, either within the, you know, the materials themselves, like a crystal, or within geometry, or, you know, within, you know, materials against materials. And here's an example just of materials against materials, but people are seeing the same type of behavior when you're getting materials against materials. Also light, you know, when you're using LEDs, you're getting some of that type of spin behavior, you know, etheric type of behavior, chi type of effect. And the example that I put some links in the Facebook account, where that you literally, you know, you could see different types of crystal formation. You could see cloudy and then clear, and the places where clear was where the pyramid was around. The pyramids, it was actually changing how the crystals formed. It was, the crystals are forming more easily wherever you had that type of etheric or chi effect or ether flow. Okay, that's the type of thing we're trying to represent, and that's what you're getting at. How do we test some type of flow? Well, there are all these different things that we're seeing out in nature at a micro level, where we're seeing, people have seen type of flow, but we don't have a good measurement tool for it. And so the freezing ice is one place that we do see that a way of measuring, okay? So you take the ice, you freeze it, and you've got some type of etheric effect, whatever mechanism, and there's lots of different mechanisms we've seen, and you try and put it next to the ice and see how the flow has changed. Does that answer your question, David?
Yeah, that's interesting. I don't see, I know a lot of people who has been doing ice work. Yeah, but I can't see the connection maybe to, it's not well explained, but.
No, it's not. I mean, that's part of the challenge. Okay, we're getting this effect. How can we model mathematically the flow? You know, and we have a lot of different mathematical tools that we can potentially use, you know, at the very simple level or the very complex level, like the CFD-RD type complexity. So, you know, which are the simplest mathematical models we can use to create, to say, okay, we're seeing flow, you know, just come up with an ad hoc technique, and okay, here's the pyramid and it's creating this type of flow, or here's, you know, the LED or the electrogravitic device, and here's the flow change that we're seeing in the ice. We're seeing that there are different places that the crystals form more easily. So that's where we're seeing more flow. This is the flow pattern. And so we're seeing all these different flow patterns using all these different devices. So can we now come up with some mathematical representation for those flows, and then, you know, step it into the full CFD RD type model? So it's, you know, experiments, and then, you know, how do we then try and model it? And there's all different types of levels of modeling.
I wanted to show the picture of the Anu. Is there a way I can put a figure so everyone can see it?
You can share your screen and just
on the screen.
Show the image on your screen.
I think it's in the middle at the bottom.
Oh, okay. Maybe everyone remembers the picture of the spin that the Besant and Leadbeater had visualized?
Yes, yes.
Called it the Anu. They had the vortex going in two different directions. The counter-rotating, like a caduceus.
Yes.
So maybe one is for the exons, the other for the ions. Like exons are coming in, ions are going out.
Has anyone described this motion in better detail or so? Except images.
Based on what they found, I haven't done much reading. I did get their book and read what they wrote, but recent investigations I haven't read.
You know, there's a smattering of ad hoc models out there where they talk about, you know, exons going one or electric flow going in two different directions. Even, you know, you take the example of wires that run power, you know, outside the telephone poles. The actual equations that they use, or one of the people claimed that the equations that they're using on a daily basis to model everything is you can't model it from, you know, one pole to the other pole and then back again, because it doesn't capture it. You have to model it as electricity going in both directions at the same time.
Can you see that share there?
Yes,
Yeah.
good to see this. Maybe you can send the link also.
The way they draw this, it looks like it goes all the way down to the bottom one direction, and then it reverses. Instead of coming out, it starts to go in again. Makes a big loop and goes in again.
So one of the things that we saw with like Pulver's experiment, or the computations there, we didn't just see two layers. We saw like 3 or 4 layers within each particle. So it might be more complex than what's represented there.
Well, I believe the caduceus part in the middle is the core of the particle, and the stuff around that, where it goes out and loops around, the larger loops, that's the shell area of the particle. So like X is, you know, let's say the electron, X is high, so it's flowing from the core to the first shell, whereas Y is flowing from the first shell to the core. So you have those two flows that this might be representing what's going on. So it might be something to think about.
Yeah, it would be good to have these flows described differently to get them even broader imagination of them. It seems like they have. Should we put any attention of like being three lanes here, and that they are like turning on the bottom? What is actually the important features here?
In this particular picture, this is just showing spin, how spin can orient particles for bonding, for nuclear bonding. So you see the triplet on the left and the singlet, both deuteron. They're just two versions of the deuteron. They have different energy levels.
Okay.
And here's the helium.
Yes. But there is that they are like on the bottom here, on the bottom left. It's different from the top. It's like they are turning. The small 3 lanes are flipped, and they are not doing that on the top. Is that some?
Which diagram are you looking at?
Diagram A, triplet deuteron.
Yeah.
Yeah, they don't look the same in the top and the bottom.
All I did is do some Photoshop. I pasted the image one over the other.
Yeah.
So if you want to see it more clearly, look at B, where you can see it's out in the open there.
I think they're just overlapping.
Yeah.
That's the difference in where they're overlapping.
The important thing is that the spin, the flow that creates a spin, is going in the same direction in both particles. That's the way they line up. Otherwise, they would conflict with each other. And when you use that reasoning, it explains everything they find, as far as these triplets and singlets.
Eh, honestly, any subparticle based, if you look at it from a subparticle interaction perspective, and you're going to have this type of, when you have this type of flow, you're going to see the same type of reasoning. So it makes a lot of sense because using the same computational reasoning at each layer, particle, subparticle, cosmic, atomic. If you've got that flow, they're going to sink in the way that Paul describes here in this book.
Are you going to model this kind of flow with a new model?
There's a slew of different ways that you can model the same thing. While if you maintain, the subparticles as being reacting particles.
What we need is some mathematical genius who can just look at this picture and say, "Oh, I know the equation that generates that."
There's probably 50 different geniuses out there with 50 different techniques of doing it. I know. I mean, that's what my specialty is in mathematics and computers. It's computational sciences, and so I've been working with the different mathematical techniques across a broad spectrum of activities. And yes, there's a lot of different ones, and they're all excited about the specific model that they're using, and they say, yes, this matches it. But you'd have like 15 different competing guys saying, hey, use mine.
Did you see that guy, Jan Rack, a professor of physics, Scandinavian University, who joined the group a few weeks ago?
Was Jan notified?
Yeah, he's joined the group, Jan Rack.
Oh, just now? Oh, okay.
A week or two ago.
He joined the group, not the.
Oh, we didn't inform him about the meeting?
Well, I put out a notice for the meeting last week. So
you included his name?
I haven't got his email. Yeah, I put the message on Facebook, so I think he saw it. I just didn't. I don't have his email, so I didn't send him an email.
Okay, maybe he didn't check his Facebook page. Okay.
Do you know?
Are we going to do another meeting soon?
Yeah. Well, I was thinking like the same time next Sunday. Or
okay, I'll make sure to send him an email to remind him.
So David, you did your presentation. Did you want to share that with the group? You want to put it up on a link somewhere, or?
Yeah, I can share it if someone wants to look at it. Sure.
Well, it's mostly just two pictures, isn't it?
Yeah, it's basically two, one picture and one text.
But you also had the link for the Gerald Pollack stuff too. So I'm just saying, as so we can have some type of record so people can go back and look what you're doing. I wanted to go back and look at your slides and take another look at them.
Okay. By the way, I'm recording this. I recorded most of the first part and most of the second part. If it should be showing.
Yeah.
Okay,
so
we can send the link if it's just posted, but as opposed to reading through the whole thing, since.
Brennan, you're recording that?
Yeah, I was recording it. So I should, if I stop the share now, it should show, yeah, it's recording.
Yeah. So could you send a copy to both Matt and Jan, who weren't able to attend?
Matt and Jan, yes, I can do that. I mean, it looked like about a third of a gigabyte for the first part.
So you caught some of it anyway.
I could probably put it on Facebook. I'm not sure if I'd be able to send it by email. I could put it on Facebook.
Oh, okay. I'll tell them to look there.
Okay. Well, I can.
Yeah. Okay. So eventual expectations or plans or so for next meeting then would to describe this this shape.
So who's going to do what in between this meeting and the next? That's the question.
Well, I was going to have a look at.
We've done something in between.
I was going to look at the ETD stepper program again, and
yes,
try and maybe search up on computational fluid dynamics and reaction diffusion. And basically, I'm just reading. I'm trying to get through the Subquantum Kinetics book to get just to recap on SQK methodology.
You have the 4th edition?
Yes, I do.
Okay.
And just kind of think of ideas of what I can do. I was having a look at Matt Pulver's C++ code and trying to see if I could understand it a bit better, maybe ways of combining it with rotary motion. So I was looking for the paper that chapter 5, reference 22 is let's see if I've got it here. I tried to look it up on my UCL account. It's on a variety of wave phenomena in chemical reactions. That was the reference you gave for rotary motion. I wasn't able to get it.
One other thing. Have anybody been able to communicate with the academic mathematicians, chemists who are working on the brusillator?
Well, I haven't made any further progress since I last spoke to the guy that you gave me the name of, and also Professor Anne DeWitt. The guy, I can't remember exactly what.
Lefebvre?
Sorry?
Lefebvre is the inventor of the brusillator.
Mm-hmm. So I could probably do that. I've got more time at the moment, so I can probably look at those emails again and maybe send them something else.
Now, since you're affiliated with the university, right, you're in a good position to be able to deal with them, because a lot of these people, they don't want to take the time unless you're with a university.
Well, I've actually finished up the job I'm doing there, although my ID card still works for maybe another year. I'm just to see how it goes. But the job that I was doing, I've finished there, so I'm looking for, not working at the moment, looking for another job soon. But my ID things should still work for a while. ID card.
And there's a couple other projects, just to mention, besides the vortical motion idea. One being the Schrodinger equation. If somebody could figure out how to write that in terms of the subquantum kinetics version of the particle, having the wave pattern in the particle. And what was the other was to be able to model charge. In the brusillator, they have the charge state where the whole wave pattern sort of gets biased away from the 0 point. And we know very little about how they did that. If there's a way to contact the people that did that, to find out, suggest to them our model and see how would they do the same thing. Maybe they have some ideas. I mean, I don't even know what the parameters were that they used for that.
So what's this again? The charge on something you said?
The charge bias state. Akhmudi, I think, is the fellow that did that. He did the mathematical analysis and showed the charge state of the brusillator.
So here's a open source CFD computational fluid dynamics system, OpenFOAM.
OpenFOAM.
Yeah, I believe that's the most popular CFD dedicated system. There, things like Blender and other computer graphics tools have CFD features in them. I think some of them even actually have some reaction diffusion in them also. But if you want, a little more directed system, I believe OpenFOAM is going to be more focused in CFD. It's also, I think, has reaction diffusion elements. I think here's some examples which have, some of them are reaction, have reactions in them, step reactions, and I think this is just one example, but I think there's some other reaction studies. Here's another reaction system, surface reactions. So that people have been, and then diffusion, I think, is on another thing that is. So here's some examples of, diffusion and reaction-based systems. within OpenFOAM. So it looks like people are successful using this tool to represent CFD along with reaction diffusion.
So are you all aware of this model, or you're hearing about it for the first time?
I think I'm hearing about it for the first time.
Yeah. This is a modeling tool.
Right. Yeah, I've got a copy of it myself. If any of you want those tools, maybe one of the best ways to get it is in a package that I have that I've downloaded myself. It's called CAE 2013, which is the most recent year, computer-aided engineering, and it's a Linux package, and it's got all those tools in it.
What's it called again?
CAE 2013.
CA.
Why didn't you just share a link in the chat? I just shared a link to the OpenFOAM stuff in chat.
I'll do that. I was looking it up, but I hadn't quite got a link yet. I haven't put it to good use yet, though, so I'm not highly experienced with it.
It takes time to get into each one of these systems. Is anybody else getting this flashing middle screen?
Yeah,
How do you turn that off?
the flash.
Yeah, it keeps
No,
flashing.
I see it on your screen. I mean, on your face. You can see the flash on your face.
Okay, does anybody else know how to turn that flash in the middle off?
I don't have a flash.
All right, maybe I'll just change the view. Okay, all right, that's a little better.
Got it? Yeah.
Huh.
All right, I put up with it for a while.
Okay. Anything else?
So you were talking about goals. I mean, we sort of talked about them last time. Everybody's still trying to get, basic idea of some of the things that they want to do. Obviously, everybody, we're sharing ideas, and everybody's got their own idea of the goals that they want to try and go towards, and we're sort of sharing goals with each other also to see what,
I think
matches
also,
we can get.
well, when one looks at the introducing spin, as such as Navier-Stokes or rotary motion, I think just by trying to get an idea of the basic equations and how to. I mean, that's for each individual to try and work out and maybe share as well. Just trying to get a grasp. When you look at Navier-Stokes, you see a whole spew of equations that looks quite complex. And the rotary motion, well, I haven't been able to find, I haven't looked a lot, but I haven't been able to find some equations on that. So I think it's basically getting an understanding, getting a physics understanding, or a basic understanding of the problem. So we've got the reaction diffusion with the Brusselator model, and now we need to bring in this rotational motion, and it's just really getting a grasp of the basic physics problem, and the equations to be used. So
last time I mentioned it is that, and I mentioned a little here, is that one of the things we're not seeing is that motion might actually be in the equations as they are. We just are not pulling that information out. We're not pulling out, I believe when I looked at Matt Polar's set, I didn't see any way of pulling out any flow from it. I only saw, quantities, how much exons, how many yons, not how is it flowing from one location to another. We only saw stability in quantity levels. We didn't know if there were exons moving in one direction within the particle or not. We only saw, okay, there's this number of exons, but was there actually a flow of those exons going in any specific direction? Was there a spin actually there? So we may be able to pull some motion out of the existing equations if we just represent or try and capture some other information from within that mathematical system that was already built.
What we need to do, I think, is simulate the model G in 2 dimensions, to be able to see if there's anything like that going on.
2 dimensions or 3 dimensions?
Either one.
We'll start off with 2 dimensions because that's a bit easier, and then go up to 3 dimensions when you've got a grasp of 2 dimensions. then go up to 3 dimensions. If you
Yeah, if you have a fully spherical symmetrical particle, you can model it to 1 dimension.
yeah,
Well, that's the thing. Matt made the symmetry assumption.
Yes.
And we don't want to make that assumption if we're going to
Okay.
see if there's any rotary motion.
Right.
That's what you're saying, right? If the model G as it is produces rotary motion.
Yeah, well, remember when you talk about model G is very broad, and the specific equations that were used, you know, is a subset of that. The successful equations that we have, maybe the successful equations we have already have motion in them. So, you know, model G and subquantum kinetics is it's a broad topic, and a lot of things can fit in within that model.
Wait a minute.
A lot of different types of
Model G,
submodels.
when I speak of model G, I'm just referring to those 3 equations.
Yeah. Okay. So that basic set of equations, obviously, there are different parameters in there. So there's like an infinite number of different things that could fit in there. So and you also talked about in your book of different flavors of those equations potentially too. You know, depending upon, you know, how many etherons you might have or that type of thing. You did talk about some alternatives. So yeah, when I look at it and say, hey, this is a broad thing. We could throw a whole bunch of different equations. We could, you know, it's a generic modeling technique, and that's the exciting part about it, is there's a lot of freedom within that big space to try and find something that matches, you know, the world out there. Forget about just, you know, the infinite number of possibilities from using the, you know, that specific subset of equations. There's a whole bunch more different equations we can potentially model using the same basic idea.
So you think, you agree it would be a good idea to do a 2 or 3 dimensional simulation to see?
Right. Yeah, with what we have existing, to see if there's some way we can tease that information out. So if we can get Pulver out there, I think he understood the equations and how they were running in Mathematica or wherever he was running them most effectively. It's, you know, there's reactions happening there. So when you write solvers, you know, one of the assumptions from the solver is, what are you trying to solve for, and what type of information is coming out? But that same set of equations we might be able to pull other information out by modifying the program, whether it's, you know, 1, 2, or 3 dimensions. Obviously, the farther direction is to go to 3 dimensions.
Is it also possible to have chemical inertia, and it may not actually be necessary to have mass inertia? You know, certain reactions take a certain amount of time. So I guess maybe call it time inertia.
Time or create force. Reactions create force in a specific direction.
Mm-hmm. So
all of those things can fit into this same model. There are a lot of different things we can play with as possibilities.
I was thinking just to not have to get into the mass topic, because then when you start, okay, well, what are the masses going to be? What are the densities?
Right. So chemical forces, mass, momentum. Number one, we're just looking at motion. You know, with what we have now. We had reaction, just the diffusion part, because diffusion, just that subset, makes certain assumptions of motion. So we are getting motion just from the diffusion element, and just using that element, that's the simplest thing. Just going with that. I mean, that's a good place to start with. We don't have to necessarily add in momentum yet. We don't have to add in, chemical force or what have you. But those are all things that could be added to more closely match, what we actually see in the real world. But just getting motion out is the number one step, in working with different dimensions.
But the 2 and 3 dimensional modeling I don't think it can be done on a laptop. You need a mainframe, don't you?
Laptops are, compared to, was it 10 years ago or 5 years or 6 years ago where Matt was doing it, the types of computation you have now are much higher. Plus, you also have droplets and a lot of other types of computer systems up in the web, in the cloud, that you can actually run this stuff on. So any code that he's written, we can take that, we can throw that up on a droplet that we just create for a short period of time and just run it. And the costs are not that high if you limit the amount of time that these things are running. You don't have to set it up all yourself. You can just grab a big thing from an Amazon a server, I mean, I do that. So that's not a huge deal. That's something that we can leverage.
Yeah, and it will be much faster also.
Mhm.
You can allocate much more cores, so you will have a much higher execution if you buy a service.
Service. You also have a lot of microcomputers now that have graphical processing units within them.
Yeah, but then you have to rewrite the code, and I think who will do that?
Yeah, I write code all the time.
Maybe it's easy. We can think about it.
Yeah, but there are all these devices that we can access now too, and even create parallel models. You can create your own little small supercomputer now. They've got this new model that's coming out that's got neural network processors for $100. And
What processor?
I don't like the term neural network because it's really, I mentioned the term gradation mathematics before. They're usually literally using linear algebra to do the equations, but it came from a model that very ambiguously modeled what neurons were behavior. But at the time when they came up with it, I knew biologists, I knew mathematicians. They say this is very far from what we actually really see. But nonetheless, that analogy has continued on for 2-3 decades. And so they call it neural networks. It's basically just linear algebra, and they're getting this gradation behavior. Remember, I was talking about you got discrete, you got continuous, but the gradation behavior is you're in a continuous space, but you get these jumps. Like with cymatics, you have sand on a sound thing, and you change the sound, and it stays that pattern for a while, but then all of a sudden it makes a jump. But there's a little play in it. It's not fixed at that discrete level. It's around that gradation level, but there's a little play. Like instead of half spin, you've got 0.51 spin and 0.49 spin. You've got that little play.
Is that similar to fuzzy set theory?
There's a lot of different mathematical techniques, including fuzzy set theory, that you can use to model gradation behavior. So we've got a slew of new mathematical techniques that are basically representing gradation behavior. So that's what I'm saying. You had discrete, you got continuous, but now we have this new gradation type mathematics, and there's a slew of different techniques that can be used to do it.
Okay, so one person will be working on writing code for the modeling, and somebody else on how to introduce motion into the equation. Is that something, two things will be going on, or what?
There's a lot of different things we can do. I think we need Matt Pulver around so we can at least talk with him about some of this stuff. If it'd be great if we could get him to just bounce some ideas off him. We obviously can see his code, but more of what we want is the lessons learned in running the code. Not in the lessons learned in the paper. Obviously, there was a lot of lessons there, but in his actual running of the code, because he was looking for specific patterns, etc. If we're to pick it up and try and do 2-dimension or 3-dimension, how would we think of pulling out motion? Because equations are typically set up to get quantities of how much. They're not necessarily set up to get the motion of the things at that level. So that might take a bit of thinking, and to see if we can actually get it out of those types of solvers. He's looked at a lot of different solvers for the same thing. So to get some insights there, bounce some ideas off of him, it would be nice.
Yeah. He'll see the recording and can know what we're talking about. Very good. So maybe at the next meeting, we can hear Matt's opinion on that.
That'd be wonderful.
Meanwhile, what will we be working on?
Well, I can eventually look further into that structure, the deuteron thing. I will try to do that.
Okay.
In other regards, I'm not sure that I can do, I feel somewhat, I have run this ETD stepper a lot, but I'm not sure I can. If someone sends me parameters, of course I can run that simulation. It takes 10 hours to do each simulation, but I feel like I have no idea how to pre-configure a run. But if someone has, send it to me and I can run that simulation.
For the 2 or 3D simulation?
3D. But
3D?
of course, 2D is better since it's much faster, but I don't, yeah, maybe that should be done.
So there's some advantages of working with the C code that Matt put together. It gives a little more freedom to make modifications, to create add-ons. So I'm not sure which version that you're working with. You know, he did the web-based one, he did the C code-based one, then he used Mathematica.
Yeah, I used the C++ version,
Great.
which is on GitHub. The first link here in the chat box.
Okay.
And that was default configured for 3D, so that's the only mode I have used. And 3D is a much more computation, so it took, yeah, I don't know, at least 10 hours to run just one animation sequence.
All right, so some of the things that we may want to do is see how we can put this up in a droplet or a
yeah, then you can do it maybe in 10 minutes instead of 10 hours if you just buy the capacity.
Oh yeah, I've done it.
Yes.
Yeah, because I couldn't run it on my laptop, the 3D. It was impossible. So,
Well, it takes, it needs a lot of RAM, 10 gigabytes. That's the only thing you need.
yeah, I was running on 3. So
Yeah, that's too small. You know.
I was able to modify with his help. I was able to run 2D, but it's been a few years. But I could, I might be able to pull some things up, but it's been a little while. But it's not that hard to do once you know how to do it.
Yeah, are we going to have any expense to do this?
if you're going to be loading it up on the web to run, there are free versions out there, but they're not the most powerful computers. But still, they'd be free, and you could run it, for however long up on the web, and it'll just be crunching out stuff. And it would, if you're using the free version, if you need the greater computation, you can potentially get a bigger one. But we can at least experiment with the free type version, and then as we're confident in the experiment we're running, then we can move to a bigger computer. We can just move it over real quick, easily.
And that's where you'd run into some expense at that point.
Yes.
Yeah.
But depending upon when you run it, if you run it for a day, that's your expense.
Maybe we can get a donation from a charitable institution to help out.
If we have a very clear concept of what we're doing, yeah, I think we can. So let's look at the C++ code. Let's everybody take a look at it and try and get a better understanding of it, since we want to focus in on that, so that everybody can be competent in it, and then see if we can figure out how to run it up on one of the servers. Set up accounts for everybody so everybody can look at their.
Well, it's good to see younger fellows take an interest in subquantum kinetics, because I don't know how much longer I'll be around.
I hope you're around a lot longer.
People are living for a long time. My uncle is 99.
Oh.
So he's got his 100th coming up in October.
It'll be interesting if Jan Rack and Matt Pulver that are here next Sunday. They might have an interesting input to give us some ideas of where to go next with this. I mean, for my part, I'm going to keep reading SQK book, basically looking at the Matt Pulver's C++ code, and seeing if I can do anything with computational fluid dynamics. Get the software set up. I just keep thinking about how can I include vortical motion into SQK as it is now.
So I personally have 3 different activities I look at. I'll look at the C code. I will also look at the presentations that I have online for the computational advantages of subquantum kinetics. I'll probably be trying to do a little more formalization of turning those into papers. So I might start writing those into an article format, and I might run that ice experiment that I told you. I've got all different types of Qi type devices and you know, pyramid, what have you, and trying those, work some of those experiments on ice in a freezer and see, you know, what types of patterns emerge.
And there's some stuff on the CSE effect. They talk about pyramid shapes or cones causing ether flows from their points.
Right. So that's one of the things is just, you know, see what, using ice as the formation as the measuring tool, see what I can get out of, you know, just some simple experiments. Like if you look at some of the videos that I referenced in the in Facebook.
I'll try and upload the video to Facebook if it fits. It's about a third to half a gigabyte.
The recording?
I think that's what it seemed to show, about 300 megabytes when I had a look at it, but I have to click on it to format it properly.
Maybe you can get the size down a little. Okay, so
simply linkable. Yeah.
Anything? So, are we bringing the meeting to a close now, or?
Michael, what did you have any idea what you wanted to work on? David, Paul?
Yeah, I'm trying to work on that structure, the lead beater fluid, vortex helical fluid structure, because I've been discussing this earlier today with someone I know. I have seen great application of it.
What type of, how are you going to try and model that structure, and what type of structure are you seeing?
Just write a simple software so that this motion can be seen and changed.
Okay, I understand it a little.
Yes.
So not quite 100% sure what you're saying, but I've got some general idea.
I think I will put it on Shader Toy. That's a great place to write small software pieces for graphical purposes.
Okay.
You can try it.
I'll probably, I don't have a whole lot of time probably coming up next week, but I can re-familiarize myself with the stepper if necessary, in case you know, that information is necessary. And I just noticed that that computer-aided engineering package was updated since I last downloaded it. So there's a 2018 version, and I might do a little investigating into that and see what updates they've had, and see and get more familiar with how those software tools could be related, incorporated into what we're doing.
Paul?
Okay.
What are you planning on doing this week? You're the one who asked the question, so I'm going to bounce it back to you.
Me? Well, whatever you guys need, you know, send me an email. Any questions, you know, I can help that way. I'm already working on a number of projects.
Right.
Yeah.
Oh, so what do you plan to share from next week? I mean, you're doing lots of stuff, so, you know, choose one of the things that you want to share for 5-10 minutes for next week. It can even be one of the articles that you put at the side in the, you know, etheric news.
Yeah, I did a posting about the time dilation effect, how we discovered it. It's on etheric.com.
I saw that.
Oh, you saw it?
Thank you for sharing. Very interesting.
I figured I had to document it for priority because at that time, as you read, there was this group in Hollywood, California, that wanted to steal the project. And fortunately they didn't find anything, and they lost interest. They didn't know how to make the device to produce the ether wind. They weren't generating any ether wind.
Well, that's
So
pretty.
what was the difference? Maybe next time you can tell us what the difference between what they did and what you did, what they were missing.
They didn't have, well, first of all, they didn't go to high enough voltage, and rise time wasn't sharp enough. You need sharp rise time.
Okay, that would be a great thing for you to give us 5 or 10 minutes next time.
Like nanosecond rise time.
Yeah, how you get that? You know, what are the different instruments that you use to do that?
And Jan and I are planning experiments in Prague later this year at a university, but the university is unaware that this is for ether. If they heard the word ether, they would show us the door, you know. So we're saying that we're doing experiments on anti-gravity or Podklanov effect. They're willing to accept that. But we're going to slip some experiments in there, like the time dilation experiment, the superluminal propagation effect. You know, as far as they're concerned, we're just measuring the speed of light. We won't tell them the results till after we get them. So yeah, so that's going on right now. I hope we'll have some data in April or May. We'll see. It takes a while to build. It's a half million volt machine they're building.
So do you know a lot about the, you know, how they're generating, you know, you get those sharp rises. Do you know how they set up the devices to do that?
Well, it has to do with the spark gap. You need a thyrotron that produces sharp rise time. And
what?
That you can help that happen
Cyclotron?
with pulse shaping network. And that shapes the discharge. So it sort of avalanches it to have a sharp front.
Okay.
I don't know much about all that, but the people making this thing will know, they understand about that. And we just give them the specs that we would like a 1 or 2 nanosecond rise time. So we hope they can get that.
Okay.
Well, by the
So
way,
maybe we'll do a Q&A on some of the topics that you have in your etheric.com. You know, any you know, if you got references to that stuff that, you know, you send them back and forth and, you know, what comes back from them, that would be interesting. I'm curious about learning more about the electromagnetic components. I'm not an expert in it. I do computers, but, you know, in computers, you do some, you know, electromagnetic stuff, but certainly not to the level of what you're talking about. It's more at the, you know, the transistor, you know, type level, you know, zeros and ones, and how do you do substrates and things like that in order to get the zeros and ones. But certainly not what you're talking about. So, and to understand what's going on with subquantum kinetics, ether, I think all of that's absolutely critical because, you know, you're working with I'll use the term gradations just to simplify everything, of, you know, how the exon, y-ons, and g-ons interact with each other, and the different gradations that they go to.
We should also consider the K constant, that it might have a component in there that depends on the ether velocity. I'm figuring that's what causes how the ether flow affects the clock rate, that it slows down the reactions through the K constant, changing the K constants.
Okay.
In Model
Because the
T.
K constants, you know, they're just a sort of a summary of what's happening at the chemical level, at least in chemistry. So, you know, all of the collisions and so on, cross sections and all that goes on to figure the K constant. We can, instead of making it a constant, we could put in a variable if we can get how they figure the K, what's involved in the K,
Okay.
and get a handle on it that way, maybe. I don't know.
Great.
but before the meeting gets closed up, just I want to let everybody know that if you want to, in the chat window, if you click on more, you can save the chat and all the links that we've posted or any of the comments in the chat room, you can save it to your file. And that way you have it for reference later.
Where is it saying more?
And in the chat area where it says, just near where it says type message here, but to the right and just above it.
Oh, okay.
Yeah.
Save chat, okay.
Mhm.
Great, thank you. I already saved it to my own tool, so I just cut and pasted it.
Okay.
Okay, I'll try and get the recordings and put them up on Facebook.
That'd be great.
Okay,
Thank you for putting this together, Brendan.
Okay, no problem.
thank you, Brendan.
Thank you, Brendan.
Okay, shall we draw it to a close now?
Think so?
Okay, good night,
Good talking to you all.
good afternoon.
Bye.
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 Bye-bye.